Day before yesterday, we have done transpose of any matrix. On the basis of transpose, we define any matrix as symmetric matrix or skew symmetric matrix. Any matrix is said to be symmetric matrix if transpose of that matrix comes out to be A. And it is called skew symmetric matrix if transpose of any matrix comes out to be minus A, that is equal to minus A. There is one more condition in case of skew symmetric matrix, that all diagonal elements are 0. So on the basis of symmetric and skew symmetric matrix, let us consider examples. Suppose there is one example, find the value of x if A is symmetric matrix. A is given as 2, 1, x minus 3, 4. As it is given that A is a symmetric matrix, A transpose must be equal to A, that is Aij will be equal to Aj for all I and j. That means A12 must be equal to A21 in this particular example. A12, that is x minus 2, should be equal to 1. From here we get the value of x as 4. One more example, find the value of x in A matrix 2, x minus 3, 4, 1, 2, x square, 4, 16 and 3. Find the value of x in A such that this matrix A is symmetric matrix. Now since A is symmetric matrix, Aij should be equal to Aj. That means x minus 3 should be equal to 1. A12 equal to A21. We get the value of x as 4. A23 must be equal to A32. A23 is x square and A32 is 16. So x square must be equal to 16. We get x equals to plus minus 4. Now here we get the value of x as 4, and on the other hand we get the value of x as plus 4 and minus 4. In such cases we have to take the common value of x. So here x should be equal to 4, as 4 x equals to 4 is common value. Let us consider one more example. Find x if A is a skew symmetric matrix. A equals to 0, x square minus 2, minus 2 and 0. We can see in this A is a skew symmetric matrix, and in skew symmetric matrix diagonal element must be equal to 0, and Second condition is that when we take transpose of any matrix, that should be equal to minus A. That means in this case, in skew symmetric matrix, A12 should be equal to minus of A21. That implies x square minus 2 equal to minus of minus 2. X square minus 2 equals to 2. That means x square equals to 4. So the value of x comes out to be plus minus 2. Here we get x as plus 2 as well as minus 2. So x can take value plus 2 as well as minus 2. Now instead of a as 0, x square minus 2, 0, we can also have a as 0, x square minus 2, minus 2 and x minus 2. In such case, as it is given that A is skew symmetric matrix, skew symmetric matrix means diagonal elements must be 0. So in that case we get x minus 2 equals to 0 and we get the value of x as 2. Let us consider one more example. These are the types of questions which can be asked in board exam. Now find the value of x such that a equals to 0, x minus 3, 0, minus 1, 0, 4 and 0, minus 4x is a skew symmetric matrix. Now as we know that it is a skew symmetric matrix, all the diagonal elements must be equal to 0. All diagonal elements must be 0. Therefore, A33 must be equal to 0. That means x equals to 0. Also, transpose of A must be equal to minus A. That implies A12 should be equal to minus of A21. A12 equals to minus of A21. That means x minus 1, x minus 3 should be equal to minus of minus 1. That means x equals to 1 plus 3, x equals to 4. In this question, we get two values of x. First value is x equal to 0 and the second value is x equals to 4. In this particular question, we get two values of x equals to 4 or x equals to 0. Here we don't have any common value. So no common value. Therefore, no value of x which makes this matrix a skew symmetric matrix. That means there is no value of x which makes this matrix a skew symmetric matrix. Now there are some theorems also related to this symmetric and skew symmetric matrix. First theorem is, let A be any square matrix then A plus A transpose is a symmetric is a symmetric matrix. A minus A transpose is a skew symmetric matrix. And A transpose is always symmetric. Now proof. Now to prove this type of questions or theorems, let A be any square matrix, then A plus A transpose is a symmetric matrix. We cannot prove it by using a particular example because it will be true for that particular, may be true for that particular example, but it should be a standardized result, that means generalized result. So it should be a generalized result, therefore we will not take any example, we will prove it in another way. Let us see in which way we have to prove it. Let us suppose that P is equal to A plus A transpose. Now we want to prove that P is symmetric matrix. So for that we take P transpose. If we get P transpose equal to P, that means the given matrix P is symmetric matrix. So P transpose is equal to A plus A transpose whole transpose. Now for solving this one, we have done one property earlier also, that A plus B whole transpose of A plus B will be equal to A transpose plus B transpose. We will apply the same property here also. So A transpose plus transpose of A transpose. Again A transpose is equal to A only. Therefore A transpose plus A, that is equal to P, which implies that A plus A transpose is a symmetric matrix. Second part, B part of this theorem. Now let Q equals to A minus A transpose. Now we want to prove that Q is a skew symmetric matrix. For a skew symmetric matrix, transpose of Q must be equal to minus of Q. Now Q is A minus A transpose. Therefore Q transpose can be written as A minus A transpose whole transpose. By using the property that A minus B whole transpose can be written as A transpose minus B transpose. By using this property, we get A transpose minus transpose of A transpose, which is equal to A transpose minus A only, as transpose of A transpose give the matrix A itself. So taking minus common, we get A minus A transpose, which is equal to minus Q. That implies Q is a skew symmetric matrix. Mind it, we cannot prove it by taking any example, because it may be true for that example, but it may be not true for any other example. C part. Let R be equals to A transpose. Now we want to prove that R is symmetric matrix. That means RT equals to R. Now we take transpose of this, A transpose whole transpose. Now earlier we have done one property, that if we take transpose of AB matrix, then the second will come first, then it will become transpose of B into transpose of A. So here A transpose into A transpose. Now this one will be equal to T, we have proved earlier also, A into AT, which can be written as R. That implies we get transpose of R is equal to R. That means A transpose is a symmetric matrix. Next theorem, if A and B are symmetric matrix of same order, then AB plus BA is symmetric. B part, AB minus BA is skew symmetric. Proof. Now A and B are symmetric matrix. We will start from the given statement only. If A and B are symmetric matrices, that means A transpose equals to A and B transpose equals to B. Now AB plus BA transpose. This can be written as AB transpose plus BA transpose, which is B transpose A transpose. We have proved earlier also that AB transpose can be written as B transpose A transpose, BA plus AB. We can change their order. AB plus BA, it can be written as AB plus BA as addition of matrices is commutative. So AB plus BA transpose equals to AB plus BA. That means AB plus BA is symmetric. B part, let Q equals to AB minus BA. We have to prove that transpose of Q is equal to minus Q, as we have to prove that Q is a skew symmetric matrix. Now Q transpose equals to AB minus BA transpose, which is AB transpose minus BA transpose. B transpose A transpose minus A transpose B transpose. So it can be written as BA minus AB. Taking minus common, AB minus BA, so this will be equal to minus Q. As we get transpose of Q equals to minus Q, that implies AB minus BA is skew symmetric matrix. There is one question of your NCERT book which is also very important. Show that transpose of B to AB is symmetric or skew symmetric depending upon A symmetric or skew symmetric. First of all, we have to understand this question. Question is, show that B transpose of B into AB is symmetric or skew symmetric depending upon asymmetric or skew symmetric. Now according to question, the given matrix transpose of BAB is symmetric matrix if A is symmetric. Second part is transpose of B into AB is skew symmetric matrix if A is skew symmetric. Now let us suppose that proving A part, let us suppose that T equals to B transpose AB. Now we have to prove that P is symmetric. That means P transpose should be equal to P. This is what we have to prove. Now taking transpose of P, that will be B transpose AB whole transpose. In case of multiplication, the last matrix will come out to be first, with second, and then this will be there. So it can be written as transpose of B, A transpose, B transpose, and transpose. So this will be here, this will be here, and this, like this. Will be equal to transpose of B, A transpose, and B. Now A transpose, as we have to prove that B is symmetric matrix if A is symmetric. That means A transpose equals to A. So we can replace A transpose by A. B transpose into A into B, which is equal to P. That means B T into A B is symmetric matrix whenever A is symmetric. Now second part, let P equals to transpose of B into AB. Now we have to prove that transpose of P equal to minus P if A is skew symmetric. That is, transpose of A equals to minus A. Now transpose of P equals to BT AB whole transpose, which is equal to B transpose A transpose B transpose ka transpose. So this will be equal to B transpose into minus A to B. That implies transpose of P equals to minus B transpose A B, which is equal to minus P. That implies P is skew symmetric. Next theorem, any square matrix can be expressed as a sum of symmetric and skew symmetric matrix. It's a theorem. Let A be any given matrix. So this A can be written as 1 by 2 into 2A, which is 1 by 2 A plus A. Now we can add and subtract another matrix in this one, B and minus B. This can be written as 1 by 2 A plus B plus 1 by 2 A minus B. Now we have already proved earlier that A plus B, this will be a symmetric matrix and this will be a skew symmetric matrix. So we can say that any square matrix can be expressed as a sum of symmetric as well as skew symmetric matrix. For example, express the matrix B equals to 6 minus 2 2 minus 2 3 minus 1 2 minus 1 3 as the sum of symmetric and a skew symmetric matrix. Here, transpose of B can be written as, transpose means row and column are interchanged. So first row will become first column, second row will become second column, third row will become third column. So this will be a matrix of transpose. Let P equals to B plus B transpose half. Now we have to prove that this P is a symmetric matrix. That means P can be written as 1 by 2 of B matrix. B matrix is 6 minus 2 2 minus 2 3 minus 1 2 minus 1 3 plus 6 minus 2 2 minus 2 3 minus 1 2 minus 1 3. Solving this we get 12 minus 4 4 minus 4 6 minus 2 4 minus 2 6. 6 minus 2 2 minus 2 3 minus 1 2 minus 1 3. That is P. Now let us take transpose of P. Transpose of P is 2 minus 2 2. Row changes into column or column changes into row. Second column is minus 2 3 minus 1. Third column is 2 minus 1 3. Either we can change row into column or column into row. We get transpose of the given matrix, which comes out to be P only. That means half of B plus B transpose is a symmetric matrix. Also, let Q equals to 1 by 2 B minus B transpose. That is half of B matrix. B matrix is 6 minus 2 2 minus 2 3 minus 1 2 minus 1 3 minus 6 minus 2 2 minus 2 3 minus 1 2 minus 1 3. We get this as 0 0 0 0 0 0 0 0 0. Now we have to take transpose of Q matrix. Half will remain half. 0 0 0 0 0 0 0 0 0 with negative sign. As here we get all the diagonal elements as 0. So the given matrix Q Q is a skew symmetric matrix. All the elements present at the diagonal position, that means A11, A22, A33 are 0. That means Q is a skew symmetric matrix. Now if we add P with Q, P matrix is 1 by 2, 12 minus 4, 4, minus 4, 6, minus 2, 4, minus 2, 6, plus Q matrix 1 by 2, 0, 0, 0, 0, 0, 0, 0, 0, 0. We get 6 minus 2, 2, minus 2, 3, minus 1, 2, minus 1, 3, plus 0. So we get a matrix 6 minus 2, 2, minus 2, 3, minus 1, 2, minus 1, 3. So that will be equals to the given matrix A. So the given matrix A can be written as a sum of symmetric and skew symmetric matrix.